Welcome to Statics 1, and welcome to my basement. We know that vectors represent quantities which have magnitudes and directions, and we use essentially an arrow to graphically represent a vector. The magnitude of the vector is proportional to the length. And you know, like when we're adding vectors, and we have, for example, the x-axis here and the y-axis here, we would look at the angle of these and the force, or the magnitude of the force, and we could then add vectors different ways. So say we have, this is F1, this is F2, then we would use the parallelogram law to, I can't quite get it here, something like that, to represent the summation of the two vectors. This is f of r. And then we had, which is equal to f1 plus f2, of course. And then we could also do this quantitatively. We could do it graphically, but we could also do it quantitatively if we knew all of these. If this was theta 2, and this is theta 1, and we knew the different magnitude of the forces, we could actually add these. But it's kind of inconvenient to do, and it can be kind of tedious, and you need to apply, as you remember, the cosine law and the sine law. There's actually an easier way of doing that. And what we're going to do is we're going to use what's called Cartesian format to represent our vectors. So Cartesian format. And it makes it a lot easier to add vectors together. So, for example, well, let me step back and explain what we mean by the Cartesian format. What we're going to do is we're going to use the rectangular components of our vector. So if we have a vector, we know that, well, for example, this vector, f of r, its components are f1 and f2 along those lines. But imagine that we, instead of using those lines, we use lines that were perpendicular to each other. In other words, we use what's called the rectangular components. So in this case, I'm going to put my f1 here, and I'm going to look at components that are aligned with the x and y axis. And I'll do these in another color. See if we have a marker that works. So in this case, imagine that we have f1 of x, and you see it's essentially aligned that f1 x. So that's the notation they use. F1 indicates the vector 1, and then you have x, meaning it's in the x direction. And then we have another component in the y direction coming up this way, and we call that f1y. Okay, and the magnitude of those is easy to find, applying a basic trigonometric relationships. So if this is theta, then we know that f1x equals f1 times cosine of theta, where f1 is the magnitude and theta is the angle between our vector and the x-axis. And f1y equals f1 times sine theta. Okay? Easily done. So now we know how to represent our f1 using these rectangular components, and it's easy to find what those are using our trigonometric relationships. So if we have a vector like this f1 in this case, and we have our unit vectors, remember a unit vector is a vector that just is basically a length of 1. And we're going to define our unit vector I in the x direction. So I is a vector along the parallel to the x-axis that has a magnitude of 1. And I'm going to define j. I'll do it over here. These are vectors, unit vectors, I and j is parallel to the y-axis and also has a magnitude of 1. So I and j are unit vectors. And it turns out that we can write our vector, and hopefully you've seen this in other classes, so I'm not going to, it shouldn't be something really new to you. So my vector f of 1 is going to be equal to the magnitude, f1x, times I, a vector. Remember, we can multiply, as we talked about before, we can multiply scalars times vectors. So that is essentially that vector, okay? This piece here is essentially that vector. And so we can add to that the other vector, f1y times j. That would be this vector. Here, f1yj. So I'll just mark these, f1y vector and f1x vector. And then if we add those together, you see that by the triangle rule, we're going to get the vector f of 1. Okay, so that's an easy way of representing vectors using our rectangular components in the y and the x direction. Again, finally, we can actually add vectors together in a very simple way. Imagine I'm going to put, just like I had here, I had an f of 1 and f of 2. I'm going to add an f of 2 vector here. And it has, you can see it has a different magnitude and it has a different angle with the x-axis, which in this case I'll call theta 2. The other one I'm going to call theta 1. All right, so f of 2 is basically just going to be equal to f2x times I. So f of 2 equals f2x times I. In other words, the x component of our vector 2 times I times the unit vector I, which is in the x direction, plus f2y times j. So f2y, that's the magnitude of the y component of my f2 vector times the j unit vector. And if I want to add these together, and I'll just write that here, f1 plus f2, and remember, we're adding vectors. We're going to equal, you can actually just add the components of the vectors. So you'll add the x component of this vector, the x component of that vector, to the y component of this vector, and the y component of that vector. So this equals f1x plus f2x times I, right, where that is a unit vector. So this is the portion in the I direction, which is parallel to the x-axis. And then we can add to that f1y plus f2y. And these, because they're the y components, we're going to multiply them by the j vector. So it's a lot easier. You can see how much easier it is to add vectors. We don't have to do a parallelogram law as we did here, graphical representation, and then solve using the cosine law and the sine law to find the magnitude and the angle of our resultant vectors. All we have to do is find our rectangular components by multiplying by cos theta, sine theta. And then you can just add the components and multiply by these unit vectors. So it's a lot easier to add vectors. So I'm going to show you an example. And this is actually taken from the textbook of adding two vectors together using this method. And it'll just, I think it'll show you quickly how much easier it is to use this technique in most cases than it is to use the technique that we used previously. So here's an example we're going to work out using Cartesian coordinates, very similar to the examples that we did before where you applied the cosine law and sine law. In this case, we have two vectors. One is 600 newtons at 30 degrees from the horizontal. And then we have a second vector at 400 newtons, and it's 45 degrees from horizontal, but pointing off to the left. In other words, its x component will be a negative value. And we're asked to find the magnitude and angle of the f of r resultant vector, which is a sum of f1 and f2. Okay, so that's what we're going to do. First thing we're going to do is to convert these to Cartesian coordinate form, and then we're going to add them, and then we're going to lastly we're going to find the angle and the magnitude of that resultant vector. So here's what we're going to do. We're going to first, I'm going to call this one F1, and I'll call this F2. And let's write these in Cartesian form. So in this case, we're going to have remember, it's in the x direction is always, if we want to get the x component, if we have an angle relative to the horizontal axis, it's always F1 cosine times the cosine of the angle. But in this case, because it's pointing to the left, we have our x component is going to have a negative magnitude. All right, so we're going to have negative 400 newtons times cos 45. Okay, that's in the I direction. Plus, and the y component is actually in the positive direction, so it's going to be 400 newtons times sine of 45 times our j vector. This is the I vector. Here's our unit vectors. I vector, j vector, and that's going to be equal to, and I'll write it here, f of 1. So we've written this vector, f1, in Cartesian form, where we have an x component times the I vector and a y component times the j vector. We're going to do the same for the f of 2. So I can write f of 2 vector equals 600 newtons times, in this case we have 30 degrees, so we have cos 30, and that's times the I vector. And then we're going to add that to that, our y component, which is going to be 600 newtons times sine of 30 times our j unit vector. So that's f of 2. So now to add these, all we do is we're going to take the two x components, we add those, we add the y components, and then we simply apply the I and j vectors where appropriate. So I'm going to write it this way. We're going to have negative 400 newtons times cos 45 plus 600 newtons times cos 30 times I. Okay, so you see I took the x, the f1x, and I added to it the f2x, which is this quantity. Here's f2x, and I added those together and I multiplied them times the I vector. And then we're going to do the same for the j vector, or the y component. So we have 400 newtons times sine 45. And then we're going to add to it this value, 600 newtons times cos 30. And we'll multiply that times our j vector. Okay, and the final result, and I'll just write down, is FR equals, and it's just a matter of putting this in your calculator and getting the result. Hopefully you do it right. 236.8 I, and I'll show you where we're going to put the plus 582.8 J. And what I'm going to do is I'm going to put the units out here. So don't forget, it's all in newtons. So we just carried over the n, the newtons, outside the parentheses. So that's the result. So we can write that in here, and let's see if it kind of, if we like it, if it makes sense. So it's 236, so it's kind of more in the y direction than in the x direction, and it's probably somewhere up here. And it kind of, yes, I think I kind of like the result, and the result should be more in the x direction because we have this 600 pulling kind of more horizontally. So that kind of looks good. This result seems to make sense. And if we did the parallelogram law, you see, and of course I didn't draw this to scale, but we would get something, well, a little different, but something similar in the ballpark. All right, so this is our example. Oh, I haven't finished the problem. Because the problem was to find the magnitude and the angle. All we found so far are the vector, but we can convert this to a magnitude and an angle, and I'm going to do this here on the right-hand side of the board. So how do we find the magnitude of a vector? It's simply the x component squared plus the y component squared, and then you take the square root, just like the Pythagorean law. Right? So we're going to have here f r, and notice I write it without an arrow, right? Just f of r is going to be equal to 200, the square root of 236.8 newtons squared plus 500, and I'll put this in parentheses too, 582.8 newtons squared. All right, if we take find that quantity, it turns out that it is 629 newtons. Okay, so that seems like a reasonable result. And to find the angle, so that's the magnitude, and we'll put a box around this. And now to find the magnitude, so we want to find this value here, essentially what I call theta r. So how do we do that? What we're going to do is we're going to use the relationship, and I'm going to write that, I'm going to draw that vector. Imagine this is my FR vector, and it has both a horizontal component and a vertical component. And here is the value of theta. So remembering that, well, first of all, realize that this is F R Y is this vertical direction, and this here is F R X, and realizing that the definition of the tangent is just the opposite over the adjacent for a right triangle. We can write that tangent of theta r equals f r y over f r x, and then we can take the arctangent of both sides. You end up with theta r equals arctangent of f r y over f r x. All right, so that will work. So all I'm going to do is I'm going to substitute in our FRY value, which is 582.8, and our FRX value in this relationship, and then we can get the value of theta r. So theta r is going to be equal to the arctan of 582.8 newtons over 236.8 newtons. And the end result is, I'm going to look it up, 67.9 degrees. Equal to 67.9 degrees. That's the angle, theta r, and that's the result. So we were looking for the magnitude and angle of that value, and in fact, we found it. So that's it. The next thing we're going to do is we're going to look at the same sort of relationships dealing with Cartesian form of vectors, but in 3D. In this case, everything we've done has been on the XY plane. We call that coplanar. Let me write that down. What we've been looking at so far are coplanar results. So they're all like on a plane, they're all in 2D. But next we're going to look at like 3D results. And it's basically the same thing with a few other little wrinkles that you need to be familiar with. So I will see you next time. Bring your questions to class, and I'll see you there. Bye.